Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the radiation pressure. So to discuss the radiation pressure in detail, we have to discuss the absorptivity and reflectivity first of all. So absorptivity is a unitless number or it is a unitless constant which is the ratio of the number of photons absorbed by any surface to the total number of photons incident on that surface. So if for example there are 100 photons that are incident on any surface, and out of those 100 photons that surface absorbs 40 photons and reflects the rest photons, so the absorptivity will be 40 upon 100, which is 0.4, and the reflectivity will be 60 upon 100 because it has reflected the rest 60 photons. So 60 upon 100, that would be 0.6. So A plus R obviously will be 1 because a surface is either absorbing a photon or either it is reflecting a photon. So this is absorptivity and reflectivity. Now we will be discussing the radiation pressure in different cases, and in the case 1 you can see that when the radiation is incident normally on any surface and absorptivity is 1 and reflectivity is 0. Now this means that this radiation is falling normally perpendicularly on this surface and all the radiations are absorbed in the surface and none of the radiation is being reflected. Now there are some symbols which we would be using. Let us define those symbols first of all. So A is the area of cross section of this beam, and you are assuming that this beam is a cylindrical beam like laser beam, and I is the intensity of the beam, C is the speed of light, and P is the momentum carried by any one photon. So first of all, let us see that if P is the momentum carried by any one photon, then the change in photon, okay, change in photon will be also P for any one photon. For one photon, the change in photon will be P because these photons are falling on this surface and they are getting absorbed directly. So they are not reflected back, therefore the change in their momentum is P. Now the total change in momentum, delta P total per unit time, will be equal to P into photon flux into area of the beam. See, we know that P is the change in momentum of one photon, and we have to find out the total change in momentum for n photons. So we know that this photon flux is the total number of photons per unit area per unit time. So you can see that this is the total change in momentum per unit time, and this is obviously the force acting on the surface, F. So F will be equal to P phi into A, where phi is the photon flux and P is the momentum of any one photon. Now you know that P is h by lambda, and this is phi and this is A, and the pressure is obviously force upon area. So F upon area will be h phi by lambda. Now if I multiply and divide with A in the numerator and the denominator, then we can see that in fact with the C, speed of light, then hc by lambda is h nu, and this is photon flux divided by C. And you know that h nu into phi is intensity of the beam. So pressure on the surface will be equal to intensity upon speed of light, I by C. So this is the relation between pressure and intensity for this case. Now let us see the second case. In this second case, all the incident photons are reflected back and none of them is absorbed. So the change in momentum delta P of one photon will be equal to 2p because the photons are falling on the surface with the momentum p, and we always know that the collision of photons with any surface or particle is always elastic. So they would be bouncing back with the same momentum p in the opposite direction. So the change in momentum of any one photon will be 2p. So by using that same process which we used in this case, we can say that the radiation pressure directly will be equal to 2I by C, because there will be an additional factor of 2. Okay, so radiation pressure in this case will be 2I by C. Now if the radiations are falling normally, and some of them are absorbed and some of them are reflected. Okay, so partially the photons are absorbed and partially number of photons are reflected. So the radiation pressure can be written as I by C is the pressure due to absorbed photons, and the fraction of photons absorbed is A, plus 2I by C is the radiation pressure due to reflected photons, into the fraction of reflected photons is R. Now let us, if I know that some of the people, some of you are not getting this point, so I would be explaining this with the example. So let us suppose that in the previous case we have incident total 100 photons in this case and 100 photon in this case individually. So we know that due to those complete 100 photons, the pressure was 2I by C when they all are reflected back, and due to those complete 100 photons, the pressure was I by C when they all are absorbed. So in this case, out of the 100 photons, let us say 40 are absorbed and 60 are reflected. So what we'll do, that first of all we know that due to the complete 100 photons, the radiation pressure when they were absorbed was I by C. So due to one photon it would be I by C upon 100, and due to 40 photons which are absorbed in this case will be I by C upon 100 into 40, and that factor 40 upon 100 is A. In the same way, the total radiation pressure due to reflected 100 photons was 2I by C. So due to one reflected photon it would be 2I by C upon 100, and due to 60 reflected photons it would be 2I by C into 60 by 100, and that 60 by 100 is R. So now I think you would be getting my point. So the pressure, radiation pressure will be I by C is common, and it would be A plus 2R. Now you know that A plus R is 1, so it would be I by C and 1 plus R. This would be the radiation pressure on the surface. Okay, and in the next case, when this radiations are falling obliquely at some angle theta with the normal to the surface, and they are completely absorbed. So let us see that the momentum carried by the photons is in this direction. So the change in momentum due to one photon in this direction will be P, because the momentums, the photons are moving with momentum P in this direction, and after striking this surface they are absorbed in the surface. So the final momentum is 0, and therefore change in momentum is P. Okay, now we see that now the area of beam is A, and the area of the surface on which they are falling is A dash. So the relationship between A dash and A is the fact that A dash cos theta is equal to A. You can see that this angle will be theta, so A dash cos theta will be equal to A. So A dash is equal to A by cos theta. Now the force acting on the surface in this direction, F, will be equal to change in momentum of one photon into photon flux into the beam area A. Okay, this is the total force acting on the surface in this direction. But we know that the pressure is due to the perpendicular force, and the formula of pressure is F perpendicular upon area. So pressure would be f cos theta, which is the component of this f perpendicular to this surface, upon the area of the surface, which is a dash. Okay, so f cos theta upon a dash is the radiation pressure, and f is p phi a upon a dash is a by cos theta, so it would be cos square theta, cancelling this a with a. So pressure will be equal to this momentum is h by lambda phi cos square theta. Again, it can be written as I by c into cos square theta, because we would again multiply and divide with c, and hc by lambda into phi is I, and this would be the radiation pressure in this case. Now in this case, when the photons are reflected back, complete photons are reflected back, and none of them is absorbed, so you can see that beam is coming like that and it is reflected like that. So the radiation pressure in this direction P, I am writing down the radiation pressure in this direction P is I by C, and obviously the force acting in this direction F will be equal to the pressure I by C into beam area. Okay, now we know that the net force acting will be 2F cos theta, because change in momentum is along the normal, so the net force will be acting along the normal, so this will be F cos theta component, and this would be F cos theta component. So the total force acting would be 2F cos theta. So net force will be 2 into I by C into A cos theta, and this net force is normal to this surface, and the pressure on this surface will be the net force, which is 2IA cos theta by C upon area of the surface, which is A dash. Now A dash is A upon cos theta, so pressure will be equal to 2I by C cos square theta. So this will be the pressure in this case. Now if some of the photons are incident partially, and in fact are absorbed partially, which means that some number of photons are absorbed and some are reflected back. So neither A is 1 nor R is 1, and A plus R is 1. So the radiation pressure will be equal to I by C into cos square theta into A plus 2I by C into cos square theta into R, and hence we can take this common, I by C cos square theta, and it would be A plus 2R. So this would be I by C cos square theta, and A plus R is 1, so it would be 1 plus R. So this is the radiation pressure acting in this case. Now in the next video, I will be discussing about the radiation force acting on a sphere, and there will be a very strange result of this concept. Stay tuned for the next video. Thank you.